Engineering specification sheets define a cable's maximum current with a fixed numerical rating. This value represents a thermal ceiling, the exact point where electrical resistance produces more heat than the surrounding insulation can safely endure. Every ampere of current flowing through a conductor generates thermal energy via I squared R loss. This heat is a direct product of the current squared multiplied by the metal's electrical resistance. Safe operation requires strict thermal equilibrium. The red arrows must dissipate into the environment at the exact same rate, shown by the blue arrows. If heat generates faster than it's absorbed, equilibrium collapses, melting the insulation. This physical limit of heat transfer is what engineers call ampacity. It is a thermodynamic rating that dictates the safe operational capacity of any electrical system. Calculating this equilibrium from scratch requires mapping the specific thermodynamic properties of the unique environment where the cable is installed. The internationally recognized standard for this calculation is IEC 60287. It utilizes rigorous thermal resistance formulas to balance internal heat generation against the specific thermal barriers of the surrounding materials. Performing these complex physics calculations for every individual circuit in a large-scale project is incredibly resource-intensive. It is generally too slow for daily industrial system design or production planning. Instead, the electrical industry uses a standardized heuristic. Planners establish an idealized base ampacity for the cable, and then apply fractional derating factors to account for real-world variables. This approach takes the best-case performance scenario and multiplies it by a series of decimals. These multipliers systematically scale down the allowed current based on specific thermal barriers. To ensure system safety, an engineer must deconstruct this heuristic to understand the underlying physical realities these simple multipliers represent. Base ampacity represents the maximum theoretical current a cable can carry under mathematically perfect, isolated conditions. This diagram shows the industry standard baseline, a single cable suspended in open air with an ambient temperature of exactly 30 degrees Celsius. In this state, thermal dissipation is unhindered. 3 internal parameters dictate this base value. First is the conductor material. Because copper has lower electrical resistance than aluminum, it generates less heat per ampere and yields a higher base rating. Second is the cross-sectional area of the conductor. A larger diameter provides more metallic volume for electron flow, which reduces resistance and lowers the heat generated at any given current level. The third parameter is the temperature rating of the insulation material, such as standard PVC or high-performance XLPE, cross-linked polyethylene. Materials like XLPE have superior thermal stability, allowing the copper core to reach 90 degrees Celsius without the insulation failing. This higher heat tolerance significantly raises the cable's base current limit. While these 3 variables define the base ampacity, they describe a laboratory environment that rarely exists in a functional industrial installation. Real-world operational environments, like a factory ceiling or a desert equipment housing, frequently exceed the 30-degree laboratory standard. Thermodynamic efficiency relies on a temperature differential. Thermal energy moves away from the core most effectively when the surrounding environment is significantly cooler. If the local environment reaches 45 degrees Celsius, engineers apply the temperature factor, or C sub T, to the calculation. As the outside air temperature rises, the differential between the core and the environment shrinks. The cable's ability to shed heat drops, causing thermal energy to build up within the copper. To prevent this buildup from melting the insulation, the electrical current must be restricted. The C sub T multiplier forces the allowable amperes down until the heat generation matches the environment's reduced dissipation capacity. The ambient environment effectively dictates the cable's electrical capacity, exerting as much influence over the system as the conductor itself. Beyond ambient air, the physical layout of the electrical network introduces further thermal constraints. Industrial installations typically bundle multiple power cables together in tight trays to maximize space efficiency. To mathematically account for the heat generated by these adjacent lines, engineers apply the grouping factor, designated as C sub G. In a tight cluster, cables experience mutual heating. The center lines are bathed in the radiant energy of their neighbors, leaving them with no path to project their own heat toward the cooler external air. This proximity significantly reduces the entire bundle's ability to dissipate energy compared to 7 individual cables spaced far apart. To survive this cluster, each cable must carry a reduced fraction of its rated current. The grouping factor lowers the electrical ceiling to ensure the collective heat doesn't cause a systemic failure. Because physical space is a finite thermal resource, clustering cables directly reduces their individual electrical capacity. The final thermal barrier is the installation medium encasing the cables. Open-air installations benefit from natural convection. However, cables buried underground or sealed in conduits face much higher thermal resistance. Placing cables inside a plastic conduit or burying them in soil introduces massive thermal impedance. The surrounding earth and the conduit walls act as physical insulators. They trap the I²R heat within the installation site, preventing it from migrating away from the conductors. A final installation derating multiplier is applied here, forcing the current down to the absolute limit that the buried environment can thermally sustain. Regardless of the cable's raw size, the installation pathway creates a permanent bottleneck that defines the system's maximum performance. This formula summarizes the physical constraints of the entire system. Actual ampacity equals the base ampacity multiplied by the temperature and grouping factors. Failing to account for these derating factors leads to catastrophic risks, including melted insulation, electrical fires, and significant power loss through voltage drop. Conversely, overestimating the derating factors results in massive economic waste. Guesswork often leads to over-engineering, where projects spend millions on unnecessarily thick copper and aluminum. Managing this equation is a requirement for manufacturing and infrastructure planning at scale. It dictates material costs and spatial requirements for every major electrical network. Ampacity functions as the fundamental mathematical bridge between physical thermodynamics and economic efficiency, ensuring both regulatory safety and material optimization in the modern world.